Assalamualaikum and selamat sejahtera. In the previous video, I have introduced three types of DC-DC converters. As mentioned, the input DC voltage can be stepped down or stepped up using the buck and boost converters respectively. Meanwhile, the buck-boost converter can perform both functions depending on the duty cycle or duty ratio. In this video, I will show you how to derive the output voltage equations of these converters. For your information, the most essential parameter used in the derivation is the instantaneous inductor current. Before we analyze the inductor current, we need to consider one assumption. Due to the large inductive size, we assume the inductor current is always continuous. Therefore, the DC-DC converters will work in a continuous conduction mode, or also known as CCM. For this simulation work, I choose to simulate the buck converter circuit. Throughout the simulation, I will measure the input voltage, control pulse, inductor current, output voltage, and output current. When I zoom the steady-state waveforms, we can see the output voltage of the converter is lower than the input voltage. Hence, the buck converter has successfully stepped down the input DC voltage. Other than that, we can see the output voltage and output current have continuous waveforms with constant amplitude and ripple free. At the same time, we can see the inductor current also has a continuous and ripple free waveform. However, when I zoom further, we can see the wave shape of the inductor current is actually zigzag. From the graph, we can see the inductor current increases linearly when the control pulse is applied to the IGBT. Meanwhile, when the control pulse equals to 0, the inductor current decreases linearly. Next, I will explain why the inductor current has this kind of wave shape. This figure shows a complete cycle of the inductor current waveform. The period, turn on time, and turn off time can be written as follows. According to the duty cycle equation, we can write the turn on time equals to dt and the turn off time equals to 1 minus d times the period. Based on the turn on time equation, we can label the x-axis like this. Next, we will analyze the characteristics of the inductor current when the controllable switch S1 is in on state and off state. When S1 is turned on, it is also known as S1 is closed. At this moment, the inductor is energizing and it causes the inductor current increases linearly. Hence, the current has a positive gradient or a positive slope. In this condition, the inductor is energizing to store magnetic field. Meanwhile, when S1 is turned off or S1 open, the inductor is de-energizing. As a result, the inductor current decreases linearly and therefore the current has a negative gradient. In this condition, the inductor is de-energizing to supply current into the circuit.